So in this video we're going to look at what we mean by rate of change in a chemical reaction. Consider, for example, I have a simple reaction. A gets transformed into B. Now, there are two ways I can measure this rate of change. I can either measure the rate at which B accumulates, or I can measure the rate at which A gets depleted. I can plot a graph to show you what I mean by this. So let me plot a graph on this side. So this graph is going to plot time on the x-axis and the concentration of, let's do B, on the y-axis. Let's also assume that I'm going to start the concentration of A at 10 millimolar and the concentration of B at 0 millimolar. So on the graph, B then starts down here because that's 0 millimolar. So as time progresses, I start making B. Over time I get maybe points like this, and eventually it levels out as it approaches equilibrium. Now if my data is good enough, I can also draw a nice smooth line through the data, and I can also at any given point in time tell you how fast B was changing just by taking the slope at that point. So this line here then I can write as dB by dt. This is the rate of change of B at that point in time. Okay. Now what happens experimentally though, that I wasn't able to measure B for some technical reason, but I was able to measure A. So what does the graph look like for this one? So in this case, still got time on the x-axis, but now I've got A on the y-axis. And this time A is now starting at 10 millimolar. So I need to start A there, 10 millimolar. And as time progresses, A starts to get consumed till eventually it reaches equilibrium. Now it may not go to zero depending on what the equilibrium constant is and what the reversibility is like, but let's say it reaches that point after some time. Again, I can, if my data is good enough, I can draw through a nice smooth curve through this. And again, at any particular point in time, I can mark that, put a straight line at that point to mark the slope, and then this slope is then now dA by dt. Now it should be clear to most of you that there's a slight difference between dA by dt and dB by dt. In particular, dA by dt is negative because it's getting consumed, whereas dB by dt is positive because it's getting made. Now this may not appear to be too important at this point, but consider the following case where the difference is more marked. So the case I want to look at here is a dimerization. So let's say I have two molecules of A combining to form one molecule of B. So we know that the rate of change of B is dB by dt, and we know that the rate of change of A is dA by dt. I also know that the rate of change of B is negative, and is positive, and the rate of change of A is negative. But what's the relationship between the two? I know that for every one molecule of B that gets made, two disappear. So that means A must be disappearing twice as fast as B. And I can easily write that down in the following way. The rate of change of A is, in terms of B, rate of change of B is, I need a negative sign to indicate the sign difference, but it's twice the rate of change of B. So this is important because if you report the rate of change in this reaction, you have to specify whether it's A or B because the values are different. If you just said that the rate of change was 5, well, we don't really know whether you mean 5 units of A or 5 units of B because numerically they're different. So this difference is very important when we come to look at rates of reaction, which we'll look at in the next slide.